Right, I think we're going to get started today. Hello, everyone. Welcome to another Consistency lecture today. I'm honored to introduce Pierre Hornych. He's joining us from France right now, so we really appreciate that. Pierre, I know it's a bit late, I think. And well, Hornych is a senior research engineer at HDR, habilitation to supervise research. And he is a former director of the University of Gustave Eiffel's Laboratory for Modeling, Experimentation, and Survey of Transport Infrastructure. His research interests include mechanical, behavior of road and airfield pavements and railway tracks, pavement modeling and design, full-scale accelerated pavement testing, pavement instrumentation and monitoring, and development of innovative transport infrastructure. So as you can see, Pierre has a vast list of knowledge and experience, and we're all very excited, I think, to hear his presentation. So let's give it up for Pierre.
Thank you, Javier. Can I start?
Yes, please go ahead.
Yes, so my presentation will be about a research topic that is recent in our laboratory, which is adaptation of road infrastructures to future mobility. And it was prepared with two colleagues, Paulina Leva-Padilla and Thomas Gabet. Sorry, it's not moving, sorry. What's happening? I cannot change the, sorry, you can see it, but I cannot change the page. I will try to share again, sorry. Sorry, now it works.
Yes.
So I'm sorry for that. So in France, as in your country, there is a rapid evolution of road transportation with the development of electric and autonomous vehicles. And this raises many new challenges. So first challenges concern the vehicles. So the challenges are to improve transport efficiency and safety and to reduce energy consumption and CO2 emissions. But there are also challenges associated with the road infrastructure because it's necessary to adapt infrastructures to these evolutions. And our research at Université Gustave Eiffel in my laboratory concerns mainly this adaptation of infrastructures and mainly impacts of new heavy goods vehicles on infrastructures. And we have worked recently in two main areas. The first is impact of truck platooning on road structures. And the second one is development of solutions for charging of electric trucks by the road. So I will address successively these two topics. So concerning truck platooning, we have worked in a big European project which was called Ensemble. If you are interested by the project, by typing Ensemble, you can find the reports on the internet, they are public. And so it was a 4-year project from 2018 to 2022 with a budget of about 20 million euros and 19 partners representing truck manufacturers, truck suppliers, and some academic partners. So the project was very vast, and its objective was both to develop the platooning technology and especially multi-brand platooning technology, which means technology adaptable to different brands of vehicles, to implement it in real experimentations on real roads, and then to evaluate different impacts of the platooning on the infrastructure, on traffic flow, on traffic safety, and also evaluate the environmental and economic impacts and benefits. And so you can find information about all this in the project, but our part was mainly on the impact on roads and also tunnels and bridges, but I will speak mainly about roads. So what is the impact of platoons on roads and especially on asphalt pavements? Because in France, we use mainly asphalt pavements. We use very little cement-treated materials and concrete pavements. So we work on asphalt pavements. So if you look at the strains produced by a platoon, you can see here an example. The strains are different from what you get under a single vehicle because you have several very closely spaced trucks. And the effect is that you have an increase of strains under the second and third vehicle due to the viscoelastic behavior of the pavement. And if there is also no control of the lateral position, you have a reduced lateral wandering with the platoon. And so you also localize the damage on the pavement. And because the real behavior is relatively complex on the pavement, we decided that it's necessary to start by doing a full-scale test to evaluate the impact of these platoons on roads. And so we did a test on an instrumented pavement in the project on a facility which is called the Idiada test track, which is located in Spain. And we instrumented a pavement structure for this test. So the pavement structure included, you see it at the bottom, 3 asphalt layers and a wearing course, a binder course, a base course. And we instrumented mainly the binder course and the base course. And we instrumented it with strain gauges and also with temperature sensors. So the objective was not to monitor rotting, but mainly to monitor the strains and then to evaluate fatigue of the pavement due to these strains. And so we had about, I think it's 30 strain gauges, which are placed longitudinally and transversally, so at 2 depths and also at different lateral positions, in order to capture also the effect of the wandering of the lateral deviation of the trucks. And so we needed also to monitor the position of the trucks. In fact, the simulations were done with trucks driven by human drivers because it was done at the beginning of the project. And the platooning control was not yet fully operational. So we did it with human drivers. And so to monitor the position of the trucks, we used laser distance sensors, and we monitored the speed, the inter-truck distances, and also the lateral deviation of the trucks during the tests. And so the idea of the test was we had 3 trucks, and the idea was to compare the effect of passages of a single truck and effects of the passages of a platoon. And because asphalt pavements are very sensitive to temperature, we did the tests at 2 different periods, in the winter and in the summer. And in each test campaign, we had different vehicle speeds. We had a lot of passes at 4 different speeds, 40, 60, 70, and 80 kilometers per hour. But we kept only one inter-truck time gap or distance, which was a time gap of 0.8 seconds. And so we recorded a lot of strain signals under the passing of these different trucks. And so here you can see examples of longitudinal and transverse strain signals at the bottom of the base course in the winter and in the summer. And here you have an idea of the effect of the platoons. So first you can see that, of course, the strains are much higher in the summer than in the winter. And then you can see that in the summer, you have increasing strains under the second and the third truck of the platoon due to viscoelastic behavior of the material. And you have also delayed recovery after the passage of the trucks that you can see here. And we also found that for our test, the transverse strains were higher than the longitudinal strains. So because we were interested mainly by the maximum strains, we looked mostly at the transverse strains. So first, just a comparison of the measurements. So here you have the maximum strain amplitudes observed under a single truck and under a platoon in the winter conditions on the left and in the summer conditions on the right. And so you can see that in the winter with temperatures around 10 degrees, where the behavior of the pavement is more or less elastic or where the viscoelastic effects are reduced, you have practically the same strain levels under the single trucks and under the platoon. In the summer, it's very different because the temperatures were higher, 27 or 25 to 27 degrees in the base layer. We had much higher strains under the second and third trucks of the platoon in the summer than under individual trucks. And if you compare the change of strain between winter and summer, the increase of strain is also much higher under the platoons than under the single vehicles due to the strain accumulation effects. So the idea then in the project was to try to model and reproduce these effects. And so first we tried to model the viscoelastic response. So we used the software that was developed in our university called ViscoRoute, which is a multi-layer viscoelastic calculation software. So it calculates the response of the pavement in 3D and the loads moving at constant speed. And the material layers can be linear elastic or viscoelastic. And for the viscoelastic behavior, we use the Huet-Sayegh model, which is a model which reproduces very well the behavior of asphalt materials. And so we first tried to calibrate the model on the measurements. And we were modeling mainly the transverse strains. And first, logically, we tried to model the response with viscoelastic asphalt layers, but with fully bonded interfaces. And we found that with fully bonded interfaces, we couldn't reproduce well the strain signals. The asphalt material properties were determined from complex modulus tests in the laboratory. But with the bonded interfaces, you can see the modeling is in gray. The strains were lower than the measured ones. And then we tried different assumptions, and we found that if we also model the interfaces as thin viscoelastic layers, we can get a much better reproduction of the measured strains, and we can get both the effect of strain increase in the second and third vehicle, and also the slow strain recovery after passage of the tracks. So we get much better results with the model with viscoelastic layer interfaces. And we calibrated this model on the measurements. And then in the second phase, we also used this model to make parametric studies to see the influence of different parameters. So here you have an example. We studied the effect of the lateral wandering on the strains. So we compared first case where the tracks were perfectly aligned with zero lateral wandering, and then where the three tracks were disaligned transversally with the lateral wandering of plus 20 centimeters and minus 20 centimeters. And you can see the effect. So the black curve corresponds to the tracks with no wandering. So you have a high strain accumulation after the passage of the second and third track. And when you increase the wandering, you reduce considerably the strains under the second and third track. And so you reduce the maximum strain level to which the pavement is submitted by spreading the loads laterally. We also studied the effect of the time gap between the tracks. So here you have simulations of transverse strains with 3 time gaps, 0.5 seconds, 2 seconds, and 3.5 seconds. And you can see that with the short time gap, you have a strong strain accumulation. And within the time gap of 3.5 seconds, which is relatively high, which is maybe higher than what you would apply in a platoon, you get practically no strain accumulation and a similar behavior to single tracks. So ViscoRoute, when it is calibrated on the results of the experiment, can be used to predict the effect of different track configurations and to optimize the track configurations to reduce the impact on the pavement. And then we also tried to predict the fatigue behavior and the platoon loading. And for that, we used a fatigue model for multi-axle loads, which was developed in our laboratory also a few years ago by Homsi. And the normal fatigue law, which is used in the French pavement design method, relates the number of cycles to failure only to the maximum tensile strain. And in this multi-axle fatigue model, you have 3 other parameters. Parameter NP, which is the number of peaks of the signal. The parameter AN, which represents the surface of the signal, which represents, let's say, the average strain intensity, and D, which represents the duration of the strain signal. And so we calibrated this model for the material which was used in the tests, and we tried to calculate the cumulative fatigue loading under platoons. And so we compared different scenarios. We compared a reference scenario with no platoon, only with individual tracks, and then 4 scenarios with platoons. In scenario 1, platoons were running only in the winter and individual trucks in the summer. Scenario 2, it was the reverse, individual trucks in the winter and platoons in the summer, let's say half of the year, during the cold period, during the hot period. In scenario 3, we had only platoons in the winter and in the summer. And in scenario 4, we had also only platoons, but with a larger lateral wandering, 40 centimeters instead of 20 centimeters. And so we tried to predict the fatigue life with these different scenarios for the pavement tested in our experiment. And here you can see the results in terms of fatigue life leading to a damage of 20%. It's a method of calculation of damage that we use in the French design method. And so you have the fatigue life, or the remaining fatigue life, because it was an existing pavement, for the different scenarios. And you can see that between the reference and scenario 1, when you have platoons only in the winter, there is no difference. You have the same fatigue life. In scenario 2 and scenario 3, where you have platoons in the summer, you reduce relatively considerably the fatigue life. You reduce almost by a factor of 2 the fatigue life of the pavement. And then in scenario 4, when you increase the lateral wandering, you improve the fatigue life again, and you are not close to the reference, but you are between the reference and the worst scenarios. So the conclusion is that the increase of pavement fatigue due to platoons is observed mainly at high temperatures, where you have these strain accumulation effects. Otherwise, the strains are the same as under an individual truck, and so there is no difference in fatigue. And by increasing the lateral wandering, you can significantly reduce this fatigue phenomenon. So we also did other simulations for other conditions, but it's just to give you an idea of the type of work that we did. So from the full-scale testing, we found that there is a significant increase of strains under platoon loading due to the viscoelastic behavior of asphalt layers. And this effect is mainly observed at the high temperatures when the behavior of the pavement is strongly viscoelastic. Then with the viscoelastic model, we found that a model with viscoelastic layers and viscoelastic interfaces reproduce well the platoon strain signals. And we were able to use this model to predict different platoon configurations and possibly to optimize platoon configurations to reduce impact on roads or to reduce maximum strains. And then with the multi-peak fatigue model, we were able to predict the fatigue and the platoon loading, and we found that there is an increase of fatigue mainly at high temperatures, and that fatigue can be reduced by increasing lateral wander and also inter-truck distances. We are still working on this project, and what we would like to do is to improve the fatigue model, because the fatigue model takes into account the multiple loads, but doesn't take into account very well the influence of temperature. For example, the fatigue at high temperature should be improved, and this effect is not taken into account, and does not also take well into account the rest periods between loads. So we would like to improve it first by laboratory testing, and then to develop a better fatigue model. And we were thinking also of trying to model the rutting under multiple loads. So now I will pass to the second part, which is development of infrastructures for charging of electric vehicles. So as electric vehicles develop, people try to find new solutions for charging of heavy vehicles. For heavy vehicles, there are several solutions to reduce their carbon emissions or their energy consumptions. It is the use of biofuels, the use of electric batteries, the use of hydrogen, and also the use of electric road systems, which can be used to charge the vehicles by the road. And in France, we are looking very seriously at this solution of charging of electric vehicles by the road. And so it consists to charge the battery by different methods to improve the range of the vehicles without the need of having very heavy or very expensive batteries. And there are three main technologies which are now tested or developed in Europe. It's conductive charging by catenaries. So it's like a train. You have catenaries above the truck. Conductive charging by the ground, sorry, using metallic rails which are in the road. And inductive charging, so by using the induction phenomenon, using coils which are placed in the road and in the vehicle, and transferring current from the road to the vehicle. And in France, we are mainly interested by the conductive charging and the inductive charging technologies. The catenaries are not very popular in France because of safety problems linked with the cables above the road, and also because this technology is not applicable to cars. It's only applicable to heavy vehicles. The two other technologies, conductive and inductive charging, could also be applied to cars. And so there is a strategy in France to develop, possibly before 2030, electric roads. And so the Ministry of Transport has defined some objectives. So in terms of power requirements, the power requirement for a heavy vehicle is a supply of power of 350 to 400 kilowatts. So it's a very high power supply. And this leads to have a power capacity of about 3 to 4 megawatts per kilometer on the motorways, because you have several trucks on each kilometer. So you need a power of 3 to 4 megawatts. And the idea also is to equip about 80% of an itinerary, avoiding certain difficult areas like bridges, tunnels, or interchange areas. And the objective, I don't know if it's realistic, but would be to develop in the first phase a network of about 5,000 kilometers of electric roads on motorways by 2030. And then in the second phase, 4,000 more kilometers by 2035. And it's a huge project because the estimated total cost of this infrastructure is between 30 and 40 billion euros. It's the same in dollars. It's almost the same cost in dollars. And so it's an enormous challenge for the transport industry to try to develop these solutions. And to promote these technologies, there are large research calls launched actually in France and Europe to develop these technologies. So for the road integration of these systems, there are a lot of challenges. It's necessary to adapt pavement design, pavement modeling, and also construction and maintenance approaches to take into account these charging systems which are integrated in the road. For inductive systems, so this consists of loops which are protected by a kind of protective box or protective block, and which are placed at low depth in the middle of the road lane, like this. So you have these blocks which are in the middle of the lane, and then they are covered by a thin surface course. Here you have an example of solution which already exists, which is developed in Korea by Olev, and which is an inductive charging system for buses. And so for this inductive charging, there are many integration challenges. So first, it is necessary to select materials which will ensure the protection of the charging system, and also which are compatible electromagnetically with the induction principles. There is a problem of charging efficiency of the embedded coils. The charging efficiency depends on the depth of installation on the coils, and also is very sensitive to the lateral alignment of the vehicles. Of course, there is the resistance to traffic loads. So these systems are embedded at low depth, and they create discontinuities in the pavement, and it's necessary to ensure resistance to traffic. With inductive charging systems, there are also heat losses during the operation of the system. So they will increase the temperature in the pavement, and they can have impact on pavement behavior. And there is also a problem of resistance to thermal variations, because the different systems which are buried in the road have different thermal properties, in particular different thermal expansion properties from the pavement materials. And if you have large temperature variations, this can create differential displacements and create cracking. With inductive charging, there is also a risk of exposure to electromagnetic fields. So the systems must be shielded to protect people from the electromagnetic fields. And there is a necessity to develop models to model thermomechanical response and also to design these systems. So the items in red are those on which I will speak a little more. We are not working on the material selection and also not on the risks of exposure to electromagnetic fields. For the second solution, the conductive solution, so it's a solution where you have metallic rails which are placed on the road surface, and on the vehicle you have a collector which collects the current from these rails. And so we have worked on a solution which is developed by a French company called Alstom. And so this solution consists of a kind of elastomeric base on which the two electrified rails are placed. And this support with the rails is embedded in the middle of the pavement lane. So you can see here an example of what they developed. So you have the two metallic rails, and you have also here a kind of metallic cable to avoid stray currents. And here you can see the elastomeric surface of the support. And you have also, of course, cable connecting the rails to the electric supply. And so you have trenches with these cables. So there are also lots of challenges with the integration of these conductive charging systems. So first, also the material selection for the rail support and also the bonding of this support with the pavement, the resistance to traffic loads, again with the presence of discontinuities, the resistance to thermal variations. There are also road safety issues because you have the metallic rails on the surface of the road. So there are problems with skid resistance and evenness of the road. In particular for motorbikes, to have these rails on the surface, it can be a problem, and it could be dangerous for motorbikes. You have also electrical safety problems because you have these electrified rails on the surface of the road, but they are electrified only by small segments, about 20 meters long. So it's not the whole lane which is electrified, it's only the part which is under the track. There are also problems of winter maintenance because you cannot use classical salt to de-ice the pavement because of the electric system. And there are also questions of road maintenance with the embedded rails, and of course, again, modeling and design of these systems. So again, I will speak only about the items in red. So for these problems of integration of electric supply systems in roads, we have worked also recently in a big European project, which is called Insight EV. So it's a European project which has a duration of 4 years from 2020 to 2023, and which has 33 partners. And the idea of this project is not really to develop new systems, but more to develop demonstrators of these systems, to demonstrate their efficiency and to monitor their performance in different countries and different conditions. So there are 7 demonstrators, and there are 2 demonstrators in France here, those called use case 2 and use case 3, which concern dynamic wireless charging by induction, either in urban areas or in interurban long distance roads. So we are involved in developing these two systems. So I will speak only about one system, about the system which is developed for urban roads. So we are contributing to the development of the demonstrator for inductive charging with 2 partners. One partner is Vedecom, who is developing the electric charging system, and the other partner is Colas, which is a big French road construction company. So the objective is to develop a 30 kilowatt power charging system designed mainly for cars and light utility vehicles. In fact, for induction, the power which can be transmitted is for the moment a little bit limited. And so for the moment, it's more suitable for cars and light utility vehicles than for heavy trucks. But the idea is also to upgrade it, to increase the power and to adapt it to heavy vehicles. So here you have an idea of the system layout. So you have these coils, which consist of copper wire protected by a box, which are in the middle of the road lane. And then on the roadside, you have the electric supply. So you have inverters, you have a trench in which you have these inverters. You have one inverter per coil, which supplies the high frequency electric current to the coil. And then you have a transformer which provides the current which supplies the whole system. And for the solution for pavement integration, so here you can see the shape, it's open. Normally the block is closed by resin, but here you see it open. So in the block, you have these loops of copper, special copper wire, which are used to create the inductive current. And you have also some capacitors on the side. And so they are embedded in this block. And so the idea is to use it on existing pavement, to create a trench in the pavement, to install the blocks in the middle of the pavement, to seal them with a special resin, which will ensure a good bonding with the asphalt layer, and then to cover it with a thin new surface layer. So here you, on the right bottom, you can see the layout of the system in the road before it is covered by the surface layer. So to develop this system, we realized that it is necessary to develop specific tests to validate both the performance of the system and also to validate the resistance of the road. And in fact, it's a very challenging task because you have to adapt the test and you have to adapt the material selection and the road design to this new system. So first we worked with Vedecom on the charging system itself. And so we did tests for testing the charging efficiency with asphalt materials, with the coils embedded in asphalt materials. And so we did it with this, here, this robotized system that you see on the left. So the bottom coils are embedded in the asphalt layer and the top coil is on this white plate and is moved by the robot arm to simulate the displacement of the car. And so we tested the performance in different conditions with different thicknesses of asphalt material and also different positions of the secondary coil, and in particular testing the effect of different misalignments between the primary and secondary coils. And so with this, it was possible to optimize the charging system. And then we had this problem of heat losses during the charging. And so to evaluate the heat losses, we did also some tests of performance of the coils, but we didn't do it with asphalt materials. We did it with a granular material because Vedecom wanted to be able to install and remove the coil several times and to change the parameters of the test. So we decided to do it with a granular material which has no cohesion because it was easy to embed and compact the material after placing the coil and then removing the coil again. And so we did also different tests with different distances, different positions of the coils, also with dry and wet material. And we, during operation, we measured at different points the temperature variations with temperature sensors. And we found that in laboratory, there was a very significant temperature increase when the system was operating, reproducing charging cycles, which would be representative of charging of vehicles on the road. We found temperature increases of 15 degrees after several hours of operation. And then we also wanted to test the mechanical behavior of the system in asphalt layers. And so for that, we proposed two tests. First, we did wheel tracking tests, which reproduce the loading by a wheel on a small scale specimen. So we built small scale specimens with two asphalt layers in which we embedded these coils. And so the wheel tracking test is a test which is normally used to test the rotting of asphalt materials and which consists in applying a wheel load rolling wheel load on a plate. And so we used this test on these specimens, and we tested different materials for the coil block and also for the resin used to seal the block in the pavement. And so we were able to select appropriate materials for the block and for the resin. And to test the bonding between the coil block and the sealing resin, which is also very important because the system will behave well only if it is bonded. We did these 4-point bending tests on specimens with 2 materials, in black the coil block material and in gray the resin. And so we tested the bonding resistance between the resin and the coil block. And we were again be able to compare different resins and to select the best possible resin. And then we tried to do modeling to predict the behavior of the system in the pavement. And so we tried to do 2 types of modeling: thermal modeling to simulate the effect of temperature variations on the systems, and also the effect of the heat generation by the coils in the pavement. And then we did also simulations to simulate the effect of traffic loading on the system. We did it first separately for the thermal behavior and the mechanical behavior and the traffic loading, but it would be desirable in a second phase to do a coupled thermomechanical modeling. So for the thermal modeling, we simulated, we were interested mainly by hot temperature conditions, because for the asphalt layer, what is important is to know what maximum temperatures will be attained in the system. And so we simulated temperature variations corresponding to summer conditions. We simulated air temperature variations, sky temperature variations, and also sun radiation. And then we proposed to simulate cycles of these temperatures to simulate daily variations of temperature. And then we added the heat loss due to the charging system. So from the laboratory test, we estimated the heat flow that would be generated when the system is in operation. And so the heat flow was about 80-90 watts per meter of length of the coils. And so we simulated this heat flow. So this is the kind of model that we simulated. So we simulated it in 2D. And here you can see the block with the coils and the pavement layers, and here the subgrade. So here is the finite element mesh. So it was a 2D finite element thermomechanical calculation. And so we simulated these cycles. So first only the temperature cycles, and then we added the induction power, and we simulated also the heat increase due to the charging. And so we tried to predict the stresses and the strains and the temperatures in the system. So here you can see what happens when the temperature varies. So if I can try to stop it, sorry. So you can see that when the temperature increases, here it's only the pavement temperature, you generate higher temperature near the surface. And because the properties, the thermal properties and the thermal dilation properties of the coil and of the asphalt concrete are different, you generate stresses and strains, in particular at the interface between the block and the pavement. And when you add the inductive charging, the temperature increase is higher. And so you exacerbate the phenomenon, you increase the stresses and strains, and you increase the temperature. So here is an example. So we tried different scenarios, but here is an example of maximum calculated temperatures. So you can see that the summer temperature generates temperatures in the top of the asphalt layers of about 50-55 degrees. And when you add the inductive charging, you can reach temperatures close to 70 degrees Celsius in the asphalt layer and even more in the coil block. So this means that in this scenario, in very hot summer conditions, you have temperatures which are exceeding the maximum temperature which could be allowed with a normal asphalt material. In France, we consider that Typically, the maximum temperature to avoid excessive rotting is about 60 degrees. So with these charging systems, you can exceed these temperature in hot summer conditions. And here you can see the stresses and strains generated. So we have to continue this work, but it is clear that you generate stresses and strains, especially at the corners of the coil block when the temperature increases. So we did also some mechanical modeling of the mechanical behavior under wheel loads. And for that, we did in the first approach 3D elastic finite element calculations. So we simulated again the pavement with the embedded coil block. And we simulated loading by a standard French heavy vehicle axle, which is a 130 kilonewton axle with dual wheels. So we simulated the properties of the different materials, and we calculated the stresses and strain fields and the heavy vehicle axle loads for different positions of the axle, positions where the coils are in the center between the wheels, and also positions where the wheels are on top of the coils or on the corner of the coils, to see the different effects when the loading is on the coils and when the loading is on the side. And so here you have some examples of calculated stresses and strains. So we look mainly at maximum principal stresses, maximum principal tensile strains. So here in the first case, the coil block is here and the loads are applied on both sides. It means it's the normal position of the vehicle when the block is in the middle of the lane. And you can see that in this case, the load is far enough from the coil and there is practically no influence of the coil on the behavior of the pavement. You get normal behavior of the asphalt pavement with maximum tensile strains here at the bottom of the asphalt layer. But when you apply the load directly on top of the coil, then you generate different stresses and strains on top of the coil and also on the corners of the coil. So the critical loading case is the loading case where the wheels are centered on the coil. So it's not the normal situation. It's only the situation where the vehicle will change position on the lane or will change lane. So in fact, the number of load applications in this situation will be reduced in comparison with the number of passing trucks. And so we tried with this mechanical model to predict the maximum stresses and strains for different wheel positions. For position 1, where the coils are in the middle of the wheel path, position 2, where the wheels are at the edge of the coil, and position 3, where the wheels are centered on the coil. And we calculated the critical stresses, so the maximum principal stress sigma 1, the maximum vertical strain epsilon z, and the maximum tensile strain at the bottom of the asphalt layers epsilon 1. And we did these calculations with different materials for the coil, and especially for the resin, which is around the coil, which is sealing the coil in the pavement. And here you can see the difference of results between a calculation with the resin called the VA60, which is a very soft resin, and another resin, which is called Plastirock, which is a stiffer resin and which has a modulus very close to the asphalt material. And what we found is that if you use a very soft resin, in fact, you have a soft support under the surface asphalt layer, and you increase a lot the strains and the tensile stresses and the tensile strains in the asphalt layer, especially for position 3, where the wheels are centered on the coil. Here you get a very high tensile stress and a very high tensile strain. But if you use a resin and a block also for the coils with a modulus very similar to the asphalt layer, with properties very similar to the asphalt layer, we have no strain contrast between the asphalt layer and the block. And then you have much less influence of the block on the stresses and on the strains. So in fact, to reduce the deterioration or to reduce the impact, it is necessary to have materials which have properties which are as close as possible to the asphalt layer. If you have a very soft material inside the pavement, you will create distresses. And again, I think if you have a very stiff material like concrete, you will create distresses. So it's a simplified approach, but it gives a first idea of what happens with different materials. But of course, it is based only on our pavement failure criteria, and this approach needs to be improved, and there is also a need to define more appropriate failure criteria for the electric road systems, in particular for interface behavior. We didn't simulate very accurately the interface behavior, and we didn't look at the failure of the interface between the coil and the asphalt layer. So just in conclusion, our first conclusion is that to study this electric road systems, it is necessary to develop specific tests and models, which are not the standard models used for pavements. And for testing, so there is a need to select specific tests to evaluate these solutions. And there is a need to select suitable materials, to evaluate both the mechanical and thermal behavior, to evaluate the behavior of the interfaces, and also to look at the thermal expansion properties of the materials. And then you need to evaluate the heat losses during charging and take into account the heat losses during charging. And we found that it is necessary, and we tried to do tests at different scales, starting with material properties, small scale laboratory tests, and then going to validation by full scale tests or full scale prototypes. And for modeling, there is a need to develop coupled thermoviscoelastic models to take into account both the thermal behavior and the mechanical behavior. And there is also a difficulty. It is necessary to define appropriate failure criteria for these solutions, especially for cyclic loading. You cannot use just the standard failure criteria for asphalt materials. And validation of the models for appropriate test is essential. And so the laboratory tests that we did were used to develop the models. And the next step in our work will be to do a full-scale accelerated test to test the inductive charging solution in full scale. So I think that this system represents a very interesting new research field for road engineers, with a lot of challenges to develop these solutions and achieve efficient, durable, and cost-effective charging solutions. And that concludes my presentation.
Thank you, Pierre. I think we have a little bit of time for some questions. Do we have any questions from the room? Chat. So we have some in the chat. Professor Razor, I think you can unmute yourself and ask the question if you want.
Thank you. I'm just asking about what the assumption was for the inductive charging and the heat loss that leads to the temperature change.
In fact, we based that on urban traffic. So we looked at the frequency that could be attained between the passage of different vehicles. And so we determined the percentage of time for which the system will be operating. It was about typically 10 to 20% of the time. And then we applied a continuous power, but reduced to reproduce the limited charging time. But it's an assumption, yeah. And it supposes that you will have many vehicles equipped with the charging system. Of course, in the beginning, you will have only few vehicles, and so the charging frequency will be much lower in the beginning.
And is that temperature you predicted on the surface or at the height?
The temperature that I showed is the maximum temperature in the asphalt layer. And in fact, it's close to the coil. It's just above the coil. The temperature on the surface is a little lower.
Thank you.
Okay, we have another question from Angeli. Angeli, do you want to introduce something?
Sure. Thank you, Pierre. It's nice to see you, and thank you for the nice presentation. I was wondering if you could give a little bit of detail on the viscoelastic interface that you included in the model, and what is the physical meaning of that?
Okay, we tried different solutions. We tried also how you call friction to model it by friction, but it didn't work. And in fact, what we did, we used complex modulus close to a modulus of bitumen, because you have bitumen emulsion at the interface. And we simulated a 1 millimeter thick layer of bitumen between the asphalt layers, bonded with the asphalt layers. And we compared the measurements. I didn't have time to show it, but we compared the measurements at different temperatures. And we got good results at different temperatures with this model. I'm not saying it's a perfect description of the interface, but it was able to reproduce the behavior and the platoon loading. And the explanation is that we think that in fact the tack coat at the interface creates some sliding between the layers. When the temperature increases, you create some sliding between the layers because this interface is relatively soft. Of course, you have also the aggregates, so you have some friction due to the aggregates. But so you have some relative sliding between the layers, and this changes a lot the behavior of the pavement and the strain distribution in the pavement layers.
I see. And then on the second project, do you intend to do a fully coupled thermomechanical analysis with that electric charging module within the pavement?
Yes, in fact, in the project, we had only about 1 year to make some first simulations because they wanted quickly to build the demonstrator. And so we didn't have time to develop a really coupled thermo-viscoelastic model, but we are still working on it. And now we are starting to do coupled simulations. To simulate first the effect of temperature, to simulate also the pavement strains and deformations under temperature variations. And you see that you have some expansion and contraction when the temperature changes. And also to combine viscoelastic behavior under loading and the temperature. So I think that in maybe the next year, we will be able to have a good coupled model.
Thank you so much. Looking forward to it.
But then there is the problem of I think the big issue is the fatigue model, because you have the temperature effects and you have the multiple load effect and rest period effects. And to have really very good predictions of the damage, we need also to improve the fatigue model.
Pierre, I did have a couple of questions about that, the fatigue formula.
Yes.
What was the failure criteria, and why should we be using the area under the curve and not the peaks?
Okay, in fact, in this project, it was based on signals recorded in accelerated pavement tests under multiple loads. And so from these tests, we tried to find different independent parameters to describe the signals. And so there was a statistical analysis, and it was found that the 4 parameters that I indicated are independent and can be used to describe the shape of the signals. And then we did laboratory tests with different combinations of these parameters and developed this model from these laboratory tests. Maybe another approach is possible, but the idea was to describe the shape of the signals by different independent parameters and to reflect the shape of different signals that you can get on a real pavement.
Okay, and how about the failure criteria that was used?
It's the French fatigue criterion that is used for design. It's based on the decrease of the stiffness. The failure criterion in the fatigue test is when the stiffness of the specimen is divided by 2, the modulus is divided by 2. So it's a strain controlled fatigue test, and so the failure is when the stiffness is divided by 2. We are also working now on other failure criteria. It's not an ideal failure criterion, but it was used in this model.